So.
Good morning, everybody. So we will continue tracking the geological record now. And I want to present you a study dealing with isotope carbon and sulfur on the Belly-Greenstone belt in Zimbabwe. So I will start with this very classical picture drawn by Castling in 2004. This showed the evolution or possible evolution of the atmospheric gases in the Earth's environment. And we're going to focus a little bit here on this blue curve, which is the oxygen concentration variation. And as you could see, there is basically two times in the Earth history. One time from the Earth's formation to 2.4 billion years ago, where the oxygen concentration was very low. This is basically an anoxic world. And at 2.4 billion years ago, there is a major rise in the oxygen concentration in the atmosphere, which is called the Great Oxidation Event. So there is many indicators for that in the geological record, and since a decade there is one which grew up in importance, which is called the mass-independent fractionation of sulfur. This is an isotopic signature. I'm not going to enter the theory today, but what you need to know is that this is defined as the cap delta 33 of sulfur. And when we look at the secular variation of this signature, you basically see that there is sizable mass-independent fractionation, non-zero mass-independent fractionation before the Great Oxidation Event, and this mass-independent fractionation signature disappears after the Great Oxidation Event. And because we know that there is only one way to produce such a mass-independent fractionation, which is UV photolysis in an atmosphere which is free of oxygen, we know that this isotopic signature basically records the evolution of oxygen concentration. So as far as you do record mass-independent fractionation, you could suggest that the atmospheric concentration of oxygen was below 10 to the -5, the present atmospheric level. However, if you look into detail in this mass-independent fractionation record, you do record some variation in the magnitude and in the sign of this isotopic signature, and especially you do see here a major increase in the magnitude of the mass-independent fractionation at around 2.7 billion years ago. So this is not really well understood what happened here, how we could change the magnitude of the mass-independent fractionation, and I will try to put a bit of insight on that. So I just before like to show you the record of the delta C13 in organic matter. So that's again an isotopic signature. I show you here the secular variation of that through the Precambrian. And that's quite interesting to see that there is also a major excursion in this isotopic record, which is around 2.7 billion years ago, that give us very low delta C13 in organic matter, which are down to -60 per mil. And these low isotopic signature are printed in several locations in the Archean craton, and they are basically interpreted as the involvement of a special metabolism, which is called methanotrophy, and which basically oxidizes a molecule of methane for its catabolic reaction, using either a sulfate molecule as an oxidant or an oxygen molecule as an oxidant. So this diagram could be then basically interpreted as an oxygen or a sulfate rise in the Archean Ocean as early as 2.7 billion years ago, which is a little bit puzzling compared to the mass-independent fractionation history. So that's the proposal. Could we try to put some further insight in the evolution of the biochemical cycle of methane, the variation in the amplitude and magnitude of mass-independent fractionation of sulfur, and a possible Mesoarchean oxygenation event. So for that, we have retrieved some rocks from the Belly-Greenstone belt, which is located in Zimbabwe, here in the southern part of Africa. We studied two formations, the Manjeri Formation, which is age of 2.65 billion years ago, and the Cheshire Formation, which is approximately 2.7 billion years in age. This is a sedimentary structure. They are really well preserved. They are unstrained. They suffer only a very smooth metamorphism in the subgreenschist facies, which is quite unusual for Archean rocks. And you could record several sediments like sand, silt, black shells, laminated limestones, and also this very nice structure which are bioconstruction and which are metafixed stromatolites. So we ran out some 50 samples. We did a bulk powder isotopic analysis. We did the multiple sulfur isotope measurements using the new build fluorination line at the Institute for Geology and Paleontology in Münster, Germany. And we used the classical technique for the delta C13 of organic carbon and carbonate, which are seal tube and GCI RMS. Okay, let's move to the result. Here I show you, this is the Mongerie formation, the Cheshire formation is up there. So for the Mongerie formation, we do record delta C13, which are around -30 per mil. This is a very classical isotopic signature. We could record this signature in a lot of Precambrian and Phanerozoic rocks. However, we have seen a lot of total organic content in these rocks because we are up to 5%, which is a bit unusual in such old rocks. If we now move to the Cheshire formation, we record a different pattern for the isotopic composition. We have a mean value which is quite lower, -41 per mil, and we do record value which are down to -50 per mil, and we record a lower total organic content amount. So this low isotopic signature, this enrichment in 12 carbon in the organic matter, is diagnostic of methanotrophy. So there is probably the involvement of methanotrophy in this upper formation. And we therefore do record the transition that argue for the occurrence of different biomass and probably reflecting different metabolic pathway in between these two formations, which is a quite fast transition compared to what we could record in the Archean formation. Okay, let's move to the multiple sulfur isotope result. So I show you here the result of the mass-independent fractionation, this cap33 of sulfur, versus the classical delta 34S. As you could see here, there is sizable mass-independent fractionation. We have a range from 1 per mil to -0.5 per mil. And what is quite interesting there is that we do also record a highly fractionated sulfide in the delta 34S index, which is down to -16 per mil. This is quite unusual, and because this is associated with negative mass-independent fractionation, which we do believe derive from sulfate from the atmosphere, we could suggest that the combination of negative mass-independent fractionation and highly fractionated delta 34S suggests the involvement of bacterial sulfate reduction. On this cartoon here is represented the cap33 versus the cap36. This is a way to see if we are facing an Archean signature, and the Archean area is defined by this red envelope here, and the data are in this area, which basically suggests that yes, this is an Archean signature and mass-independent fractionation are sizable. So we still are in an anoxic atmosphere with an oxygen concentration below 10 to the -5, the present atmospheric level. If we now look at the Cheshire formation, again, the situation is a bit different. We have only positive cap33 of sulfur, mass-independent fractionation, and the range of fractionation for the delta 34S is quite narrow, between 2 and -2. However, for the cap33, cap36 systematic, we still have this Archean signature, suggesting that there is no oxygen in the atmosphere at that time. So again, we do see a transition in the multiple sulfur isotope systematic between these two formations that basically argue for a change in the atmospheric and biological sulfur cycle between these two formations. So we have tried to see if we could explain all this observation by one mechanism, and I'd like to discuss a little bit on this modelization done by Domagal and Goldman in 2008. So the color code is represent the intensity or the magnitude of mass-independent fractionation production. So the warmer color you get and the more mass-independent fractionation you could record in the sedimentary record. And this is plotted as a function of the concentration of methane and carbon dioxide in the atmosphere. And the basic idea of this paper was that if you decrease the concentration of methane and if you decrease the methane-carbon dioxide ratio, you could rise the amplitude of mass-independent fractionation. So therefore, the methanotrophic activity, acting as a sink for methane in the environment, could trigger a rise in the mass-independent fractionation signature. So this is where I want to come. Recording these two transitions here in the carbon cycle and in the sulfur cycle at around 2.7 billion years, we could kind of draw this very simple scenario where we have a methanotrophic triggering activity in the upper formation, which change the methane-carbon dioxide atmospheric ratio, and which in turn could increase the mass-independent fractionation record in the environment. So that's also quite interesting because if you do that, and because we do record methanotrophy and bacterial sulfate reduction, we need an increase in the oxidant availability in the ocean at that time to trigger these two metabolism. Okay. So I will move to the conclusion. So for the mass-independent fractionation index, they are small but significant. So yes, the atmospheric concentration of oxygen, if you do believe mass-independent fractionation, was low. There is a possible link between the increasing mass-independent fractionation after 2.7 billion years and the methanotrophic activity as a feedback loop, and that could have influenced the atmospheric chemistry and properties such as thickness. And we could also say that because we do record from the isotopic signature methanotrophy and bacterial sulfate reduction, there was probably a sulfate increase in the environment at that time. And that increase appeared some 4 million years ago before the Great Oxidation event. So we do start to see oxidants in the environment.